Right, the first question on this exam is finding the pH of an acid. Okay, this acid is phenol. On the exam, you'll do the same thing, but the acid is boric acid. But you do the same thing regardless of the acid. Why will you do the same thing? Because what is phenol and what is boric acid? Is it a strong acid or a weak acid? All right, so anytime there's a weak acid, you're going to do an ice table. And this phenol could be a source of protons. So the first thing you want to do is write the Ka. Okay, the value of the Ka is something I'll give you, but you're going to write the Ka for phenol. And like I said before, it is a source. It is a source of H3O+. So this is the equation that gives you the source of that proton, H3O+ or H+.
So if we write out the equation, it's always going to be plus H2O, correct?
Yes, for Ka and Kb. But this is Ka. And then phenol may, okay, it's a weak acid, so it'll give you the proton, and you'll get H3O+. And the conjugate base. Okay, do you know what the conjugate acid, conjugate base pairs are? What are the partners? Right, this is aqueous. Right, so phenol is a weak acid, so that's going to be the acid. What is its conjugate?
C6H5.
Correct. And then this takes the proton, so those that take the proton are called a base. And what is its conjugate acid? That. Okay. Sometimes the way I teach this, I also call this proton. So the way I'm teaching it to you, these are synonymous. All right. So you have a bottle of phenol. That bottle of phenol just doesn't have phenol. Okay, because of its reaction with water, it can give you H3O+ and the conjugate base C6H5O-. Okay. So we don't care about water, because it's a liquid. So minus X plus X plus X. All right, so you'll do the exact same thing here. 0.025 minus X plus X plus X. All right, so this is initial, this is the change, this is at equilibrium. So at equilibrium, we'll plug it into the equilibrium constant. So Ka is going to equal to H3O+ times C6H5O- divided by C6H5OH. All right, Ka is 1 times 10 to the minus 10. Okay, H3O+ is X. C6H5O- is X. X times X is going to be X squared. And this is going to be 0.025 minus X. Okay, so we'll do something called a low ionization assumption. We're going to solve for X, but we'll make our life a little bit easier by doing what's called a low ionization assumption. So 0.025 minus X is going to be about 0.025. Okay, everyone see that? So 1.00 times 10 to the minus 10 equals X squared divided by 0.025. Okay, now we can solve for X. 1.00 times 10 to the minus 10 times 0.025. Okay, we will square root that to give you X. All right, just to save us some time, I already did that calculation. And I'm getting, now you want to put the units here, 1.58 times 10 to the minus 6. Okay, so just check my calculations. Even if you get the calculator wrong, if you show all this, like the pipeline, the flow through, or the thought process, I will definitely give you points. I'm looking to always give points. Okay? As long as the science is right. Hey, even I make calculator mistakes. All right, what does this X really symbolize? Yes, okay, very good. This X is actually H3O+. It's also the conjugate base. But the question is, what is the pH? And we know the equation pH is minus the log of H3O+, which is minus the log of x. We found x to be 1.58 times 10 to the minus 6. And I'll just give you that on my calculator. I'm getting about 5.80. Okay. So this is the first question on the exam. Okay, this is what you need to do. Okay, you'll work on boric acid, okay, which is also another weak acid. Okay, how do you know all of these are weak acids? Number one, you look at the Ka. It's so small. 10 to the minus 10 is like puny. But another reason is that it's not strong and weak because we know 6 strong acids. Okay, there's 6 of them. And that will take us to page 2 of our notes, of our practice test. Okay, so any questions or comments? So this is the pipeline, or the flow chart on how you do this type of problem. Okay. How do you know that something is strong or weak? Let's take a look at question 2 here. What is the pH of a bottle of 0.25 molar HCl? Okay, will we use an ice table here? No. Okay, we can just plug it in. Why can we plug it in? Okay, because this is a strong acid. Okay, strong acids, it's a direct, a very straightforward source of H3O+. Okay, so the acids are HCl, HNO3, H2SO4, HI, HBr, and perchloric acid, which is HClO4. Okay, if you see any of those acids, you can plug it into the pH equation, and I'm getting 0.60. Okay, does pH have units? No. Okay, pH does not have units. It's a scale. Okay, it's a scale. Okay. And the scale goes like this. Okay, 7 is considered neutral. And anything below 7 is considered acidic. And then anything above 7 is considered basic. Right, how about a pH of a bottle of lithium hydroxide? Okay, can I plug this into the pH equation? Okay, what is lithium hydroxide to you guys? Lithium hydroxide is ionic, so in water it will be Li plus and OH minus. And what do you think this is? Weak base, strong acid, strong base, strong. What would it would be? What? This would be a strong base. So just like a strong acid, we'll plug it in, but we won't plug it into pH. What will we plug it into? In this case, it's 0.125. Okay, so strong bases, you plug it in straight to the pOH equation. And just to save us some time, I did that. You can check my calculations later. I'm getting 0.90. This is not the answer. Okay, what is the answer? How will we get pH? Okay, what's the relationship? pH plus pOH is equal to what number, Bailey? 14, but to get the pH, we'll subtract from 14 and get 13.10. Okay. So difference between this problem and the previous problem, strong acid, strong base. The very first problem, weak acid. You have to go through an ice table, and you can use the low ionization assumption. How about this one here? Okay, similar type of problem on the test. It's telling us the pOH, the power of the OH, is 11. And it's asking us to calculate the pH of the solution. This should be easy. What's the pH? What's the pH of this? What's the pH of the solution? You could have just handed it out, but no. What is the pH here? If the pOH is 11, what's the pH? Okay, very good. 3. All right, 3. All right, because pH plus POH is equal to 14. All right, calculate the hydrogen ion concentration in this solution. The hydrogen ion concentration is H plus. How will we do that? Okay, there's two ways we can do that. We have pH is equal to 3. Do you guys know how to back calculate? Okay, so you're going to do the anti-log on your calculator. So that's 10 to the power of minus pH. And they tell us here the pH is 3. So 10 to the power of minus 3 is going to equal to 0.001 molar. Okay, we're going to put units here, right? Okay, if you don't put units, I will take off half a point or something. Okay, I'm going to put the units in. All right, so anti-log. Okay, you're going to take the second button and log, or you'll take the shift button and log, and then minus the pH. And in this problem, the pH was 3. And you get 0.001. Okay, you want to put the units. Okay, customary units are molar. Okay, calculate the hydroxide ion concentration in this solution. How will we do that? Okay, there's two ways we can do that. POH is minus the log of the OH minus concentration. And so we're going to back calculate it. So 10 to the power of minus POH is equal to the OH minus, and that is equal to 10 to the power of minus 11, and that is 1 times 10 to the power of minus 11 molar. So this is just getting you to back calculate going from pH to H plus concentration, or going from POH to the OH minus concentration. Remember, lowercase p is power. Okay, power, and there's no units. Okay, there's another way to solve for this. I don't know if you know this, but the concentration of H plus times the concentration of OH minus equals 1 times 10 to the minus 14. This is called KW. So you can use that equation to solve for H plus or OH minus. So either or. All right, finally, is this acidic or basic? What do you guys think? pH 3, POH 11, acidic or basic? This will be acidic. You can go by your pH being below 7. Okay, acidic here just means that the concentration of your proton is greater than your concentration of OH minus. Okay, so if that balance is skewed more towards H plus, you have something that's acidic. Okay, in other words, we're looking for a pH below 7. Okay, don't want to confuse you, but a pH below 7 also corresponds to a POH above 7. Okay, so if you're confused about that, just remember pH below 7 is acidic. Any questions or comments here? All right, so let's move on to the next page here of our practice exam. So do you guys know how to write KB and KA equations? Okay, what does the B stand for here? Okay, the B stands for base. Now in this problem, we are asked to write the equation for the KB, okay, which means we have a weak base. Okay, so the B stands for base. What will a base make when it reacts with water? OH minus. Okay, what will an acid make when it reacts with water? H3O plus. Okay, so this is KB. So we're going to take this weak base, which is HCO3 minus. Okay, it reacts with water. It's a KB. B stands for base, as you guys correctly stated. So anything that is a base will be a source of OH minus. Anything that is an acid will be a source of H plus. The KB tells us this is a base. Okay, what will the base do? Okay, it's going to, bases give away protons. Okay, acids take the, no, okay, blah, blah, blah. Erase, 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 okay? Bases take protons. What do acids do? Donate. Okay, so who gives protons? Acids. Who takes the protons? Bases. Okay, bases are the taker, acids are the giver. Okay, and now when this gives away a proton and bases take the proton, you're going to get OH minus. Going to get the conjugate acid for this. Okay, the conjugate acid for this is H2CO3. Okay. So this is the KB. Okay, don't get confused. Okay, don't have a mental lapse like I just did. Okay, the base is going to take the proton, so we're going to call this the conjugate base. Okay, what is the conjugate acid to this base? H2CO3. Okay, water acts like the acid in the sense that it donates a proton. And what will you get as its conjugate? This. Right, so this is the KB. Okay, this is the equation for KB. So on the exam, whatever KB I give you, okay, whatever chemical I give you, that's the weak base, it's going to do something like this. Okay, you want to make sure the base gives rise to OH minus. All right, let's contrast this with weak acid Ka formic acid. Okay, I want you to compare this with that. Okay, so what will a weak acid do? Okay, if a weak base can react with water to give you OH minus, what will a weak acid do? It will react with water to give you H3O plus. Okay, so check out this. All right, so here we have the acid giving the proton. Above, we had the base taking the proton. Do you see this? That's the KB, the base taking the proton. Here in the Ka, the acid giving away the proton. Both of them involve water. And then what you will get is H3O plus. Okay, plus HCOO minus. All right, can we do the same thing here now? Can we identify the conjugate acids and conjugate bases in this, the Ka? All right, so we know formic acid is an acid, so that's going to be the conjugate acid. What is its conjugate base? Okay, the conjugate base is formate. Okay, you don't need to know that, but this is called formate. This is formic acid. And what's the conjugate acid-base pair here? Okay, this is going to be the conjugate base, and this is going to be the conjugate acid. H3O plus is acid, OH minus is base. All right, so this is how we define a Ka. below, and this is how we define a KB above. All right, any questions or comments here? All right, the next section here is ranking acids. Okay, so you're given a list of acids. Some acids are more potent than others. Some acids are more stronger than others. So the way we assess for strength of an acid, so how is an acid strong? Its ability to give away protons. The ability to give away protons. Some are just better than others. Okay, that power is assessed through Ka or pKa. So pKa, that lowercase p stands for power. So this is going to be minus the log of Ka. So really quickly, what we can do is just do minus the log of Ka for all of these acids. Okay. So let's do it really quickly. Minus the log 7.2 times 10 to the minus 4. Okay, 3.14. Okay, minus the log 1.9 times 10 to the minus 4. 10 to the minus 5, excuse me. 4.72. Minus the log of 0.16. 0.80, rounding. Okay, minus the log of 3.5. Times 10 to the minus 8. 10 to the minus 8 is such a small number. 7.45 or so. 7.46, 7.45, 7.46. 6.2 times 10 to the minus 10 minus the log of that. Ten to the minus 10, that's really small, 9.20. And then finally, minus the log of 4 times 10 to the minus 4 for nitrous acid. .39, I'll call it 3.40. All right, so what does the ranking of this mean? Okay, so you got to do minus the log of all these numbers to get pKa. And then the rank. Okay, so we will rank the least acidic, we'll rank that number 1. And most acidic will rank that number 5, according to this, least to most. All right, so what would be the most, or what would be the least acidic? The way this works is the least acidic is your Ka is really low, okay? But when you do minus the log of that, it turns out that pKa comes out really high. Okay, this is something that's not very acidic, least acidic. The most acidic would be the opposite. Okay, the Ka is really large. Okay, imagine if you had a Ka of 1,000,000. Even though K has no units, Ka has no units, but imagine if I gave you $1 million, would that make you move forward or backward in life? Okay, for most people, you move forward if I just handed you, $1 million. So imagine the Ka, which is not no units, is 1,000,000. Okay, that's really moving forward. So really moving forward means it's really, really good at giving you proton for the Ka. Okay, so when you have a large Ka, it just means your pKa is low. All right, so however you want to rank them, either by Kas or rank all the pKas, it should be the same. So least acidic, 10 to the minus 10. Okay, what's next? 10 to the minus 8. What's next here? 10 to the minus 5. And then what's next up here? 7.2 or 4. Least acidic. Okay, so low, low, low. Okay, this one is the next lowest. This one is the next lowest, and this is 1, 2. This is the highest. Okay, number 6. Okay, so ranking 6 acids, this is what I'm getting. Okay, make sure you know. Yeah. Okay, am I right? 1, 2, 3, 4. Okay, 1, 2, go down, go down, go down, go down, go down. Yeah, is this right? Yeah. Okay, this is how you rank them. I got a little confused between these two. So highest to lowest, and I'm also confused with that least to most acidic. So just clear it with your mind. Okay, everyone understand this?
Wouldn't HClO, isn't that one lower than H and 3?
No, this is it. Which one?
Oh wait, I see it.
Yeah. So you want to go from the highest Ka will be number 6, the most acidic. And the lowest Ka will be least acidic. Okay? And then you kind of rank them according to Kas or pKas. Okay, so yeah. Okay, does this make sense? Okay, either you're going to rank them according to this way or according to that way. All right, so something like this on the exam. Okay, you'll either rank them according to the Kas, or you can rank them according to the pKas. All right, either or is fine. Okay, checking the time here, 9:57. Yeah. All right, next question here on our list. So we got to rank some acids. Okay, the strength of the acids. Okay, and this is how you evaluate the strength of an acid. All right, how about this one here? Calculate the pH of a solution made by adding 35 mLs of formic acid. I'm going to call this a weak acid with 30 mils of NaOH. Okay, so this NaOH is a strong base. It really is Na plus and OH minus. All right. So we're going to react this weak acid with this strong base. When you do that, this is the formula you'll get, or this is the reaction you will get. Okay, OH minus is a base, so bases abstract or take protons, and this will give you HCOO minus, the conjugate, as well as water, H2O. Okay. This is the reaction between formic acid and sodium hydroxide. Okay. This is the reaction between HCOOH and sodium hydroxide. All right, the next thing we will do in this type of problem is calculate the concentration after mixing. We're going to calculate the concentration after mixing. Let's do that right here. Okay, after you mix the two. So we'll first do the OH minus. Okay, I got 30 mLs times 0.1 molar. Okay, what's our total volume here? 65 mLs. Okay, very good. So this is the concentrations after you mix these two together, formic acid and OH minus. Total volume is 65. I'll just go ahead and give you that value. I'm getting 0.0462 molar. Okay, don't forget here the mLs and mLs cancel. So this is going to be 0.0462 molar. Okay, 0.0462 molar. All right, now let's do the same thing for HCOOH. Okay, HCOOH, we got 35 mLs times 0.1 molar. Okay, what's my total volume? 65. All right, 35 times 0.1 divided by 65. Let me just verify this here. Meaning 0.0538 or so. 0.0538 molar. Okay, so that is formic acid. So a question for you guys is, how much of this base will eat up this weak acid? How much? All of it, because it's strong. Okay, how much is all of it? Minus 0.0462. We don't care about liquid water. Okay, so this will be 0. This will be 0.0462 molar. And then 0.0538 minus 0.0462, I am getting 0.0076 molar. All right, so even though it's not given to us in this problem, there's two things that I will give you on the actual exam. One is the Ka for the acid. Okay, in this case, it will be another weak acid, but not formic acid, just another weak acid. I'll give you the Ka of that. But the Ka for this specific acid, I'll give this to you, is 1.78 times 10 to the minus 4. All right, so how will we calculate the pH? Okay, we have a little bit of an acid, we have a little bit of its conjugate, so we'll use the Henderson-Hasselbalch equation. Okay, so I'll give you this equation on the exam as well. You do not have to memorize it. Its pH is equal to pKa plus the log. We'll drop the acid. Okay, we will drop the acid. So I'll give you this, I'll give you that. Now all we got to do is plug everything in. Okay, minus the log of 1.78 times 10 to the minus 4. Okay, plus the log of, what's the concentration of HCOO minus? Okay, 0.0462. What's the log of HCOOH? 0.00760. Alright, so I'll just go ahead and tell you what I got on my calculator. Minus the log of 1.78 times 10 to the minus 4. Actually, I'll just do it. Minus the log 1.78 times 10 to the minus 4 is 3.75. Okay, how will we do the log of this fraction on our calculator? Okay, so we'll take 0.0462. Okay, divided by 0.00760, and then log that thing. 0.784 or something like that. 0.783. We'll just do 0.78, I guess. Whatever. Okay, not a big deal. All right, we'll put this to 3 sig figs, though I'm not a stickler for that on the exam. You don't. Okay, so you don't write all digits on the test. Okay, 3 sig figs or 2 decimal places should be enough. So 0.784 plus 3.75. I'm getting about 4.53. Okay, so this should be our answer. So that's how you approach this type of problem. 10 o'clock, 10:04. Okay. All right, so make sure you're good and comfortable and confident doing this type of problem on the exam. It will be a different weak acid. Okay, it will be a different weak acid, but it will be a weak acid. All right, now we'll move on to the next phase, next topic that we covered, which is chapter 16, and that is KSP. So this one is asking us to calculate the KSP expression for silver 1-phosphate. So silver 1-phosphate is nothing more than silver ions plus 1, and phosphate, if you remember from Gen Chem 1, is -3. All right, so KSP is used for what we call sparingly soluble solids. Sparingly soluble solids, which means we have Ag3PO4 solid. Okay, it's going to, some of it will go back, and it will give you Ag plus PO4 -3. Okay, so I will take off points, some points if you don't have the solid in there, and if you don't have aqueous, because that's important for the KSP equation. Okay, so make sure you have your proper, states. All right, next thing, what do we do in all our equations? Okay, so we gotta balance it. Okay, 3. Right, so what's +3 -3? 0. +3 -3 is 0, and this is 0. There's no charges. So that's the KSP chemical reaction. The expression for this is this. It's going to be products over reactants. Okay, why do we cube this?
Because the coefficient for silver is 3.
Because the coefficient for silver is 3. That's exactly correct. Very good. So this is what you want to write on the exam. This is the actual expression, but okay, you need the equation first as well. All right, so we have 2 more problems to go. Okay. And let's go ahead and do those. So now it's a KSP, but we're doing a KSP in the presence of not water, which was usually how we solve them, but in the presence of a different type of solvent, 0.1 molar sodium carbonate. Okay, and solubility here is given to us as S. S. All right, so we have silver carbonate solid. That's what silver carbonate is. Some of it will go back. Okay, do you know what silver carbonate is composed of when it breaks down? Okay, Ag is actually usually +1. And then when you deconvolute it or reverse engineer this, there's something called carbonate ion, which is CO3 and -2. Okay, you guys remember carbonate ion? Carbonate. All right, but see, sometimes this in water, this solid silver carbonate will go back to its component ions. Okay, and what do we need to do? Okay, we need to balance it. And now some of it will go back this way. Okay, that is in essence what a KSP is. So some of this will go back this way, and this is going to be plus 2s, not s, but plus 2s. And this will be s plus what else? Okay, this is not in water. This is in 0.1 molar sodium carbonate, which actually in water goes down to its ions, so it's going to be s plus the 0.10. Okay? What we will do is we will call CO3 minus 2 the common ion. Okay, the common ion. Okay, also known as the common ion effect. Okay, so now we'll plug that into our KSP. Again, I just want you guys to have the correct states on the exam. So KSP is going to be Ag plus squared times CO3 minus 2. All right, so I'll give you the KSP for this. We're trying to solve for S. 8.10 times 10 to the minus 12. Okay, so this will be 2s, and then that's squared, and then this would be s plus 0.10. Okay. All right, so what we can do here is we can assume s is small. So that s plus 0.10 is about 0.10. What we're saying is that there's two sources of carbonate. There's two sources of this. One is this reaction going back, which is S, and the other one is from the common ion, okay, which is 0.10 molar. But what we're saying is that most of the carbonate is coming from 0.10 molar. Okay, very little of it is coming from the back reaction. All right, so when we simplify, this becomes 8.10 times 10 to the minus 12. Okay, 2s whole squared is 4s squared times 0.10. Okay, so now we will solve for s here. 8.10 times 10 to the minus 12. Okay, divided by 4 times 0.1 is 0.40. All right, and this will be our answer. I'm getting 0.00045. Let's see here. 1, 2, 3, 4, 5. So 4.5 times 10 to the minus 6. 4.5 times 10 to the minus 6. Here. Is that what? Is that the answer? Let me try it again. 8.10 times 10 to the minus 12 divided by 0.40. 4.5 times 10 to the minus 6 molar. Okay, so that's your solubility. So if we want to complete this problem, the solubility of the solubility of, let me just write the final answer here. The solubility of Ag plus is going to be 2 times that, so that's going to be 9 times 10 to the minus 6 molar. And the solubility of CO3 minus 2 is going to be 4.5 times 10 to the minus 6 plus 0.1. And I'd like to convince you that it's just going to be 0.1. Okay. So 4.5 times 10 to the minus 6 plus 0.1, if you do it on your calculator, it's 0.1. See, you're adding a very, 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 very small number, solubility, to the overwhelmingly dominant common ion, 0.10 molar. So this is the answer. All right, let's do one more problem here. Will a precipitate form, so the answer is yes or no, if 20 mils of 0.01 molar silver nitrate is added to 5 mLs of 0.2 molar sodium chloride? And they tell you here the KSP of silver chloride is 1.6 times 10 to the minus 10. All right, so we first start out with writing the KSP equation. AgCl, some of it will go back to give you Ag plus aqueous plus Cl minus. Okay, so some of it will go back, and that's going to be plus S, and this will be plus S. And we want to ask ourselves, is this enough Ag plus and this enough Cl minus to precipitate AgCl? So we'll do the concentrations after mixing. We'll do that somewhere at the bottom here. We'll first do Ag plus, which is sourced or originates from silver nitrate. This will be 20 mLs times 0.01 molar. Right, 0.010 molar. What's our total volume? 25 mLs. Okay, so everyone realized the mils cancel. So what's 20 times 0.01 divided by 25? Getting 0.008 molar. And then we'll do the same thing for Cl minus. And what do we have here? We have 5 mLs times 0.2 molar divided by 25 mLs. Okay, 5 times 0.2, is that 1? 1 divided by 25, what is that, 0.0065, 625, something? No, I was way off. 0.04, okay? See, I can't do mental math. 0.04 molar. 0.04 molar. All right, so our KSP here is this. Okay, so we have 1.6 times 10 to the minus 10. Okay, this is S, but for Ag plus we'll substitute in 0.0080. And for this S, we'll substitute in Cl minus 0.040. Okay, I can automatically tell you they don't equal each other. What is this going to be? 3.2 times 10 to the minus 6. Let's see. 3.2 times 10 to the minus 4. Okay, Okay, so 3.2 times 10 to the minus 4 does not equal to 1.6 times 10 to the minus 10. Okay, so what's going on here? Okay, which way will this reaction go? Shift. Okay. Which way will it go? All right, so the way we will figure that out is we're going to put Q first. Okay, which one is Q here? Okay, well, this one is K because that's given to you, KSP. So we'll put KSP last and we'll put Q first. KSP is given to us in the problem as 1.6 times 10 to the minus 10, right? And this Q is 3.2 times 10 to the minus 4, which is bigger? Okay, which way will the reaction shift? Where do the alligator jaws point? This way, so they point towards the solid, and the answer is yes. Okay, a precipitate will form when you combine this volume and this concentration of Ag plus with this volume and this concentration of Cl minus. All right, so those are the main computation calculator problems for the exam. I just gave you some summary notes of all the equations that we covered in this chapter 15 and basically chapter 15. All right. And then a couple of other wrap-up points here is just some true-false. Make sure you recognize units. All these guys don't have any units. Okay. Conjugate acid, conjugate base pairs, So this is a base. So what would its conjugate acid be? Okay, if you want to get the conjugate acid, you add H+. So what would that make the conjugate acid be for ammonia? Okay, ammonium ion. Okay, do you know how to do the acid-base pairs? Okay, what would be the conjugate base? Okay, conjugate base for HSO4 minus. Here, if they're asking for the conjugate base, you remove a proton, and then that will give you SO4 minus 2. Okay? But HSO4 minus can also take a proton, and what would its conjugate acid be? Sulfuric acid. Okay? Water has its conjugate base, which is OH minus. That is when you remove the proton. Okay. Water has its own conjugate acid. Okay. That is when you add the proton. Okay. So basically what I'm telling you guys is make sure you know how to calculate the conjugate acid and conjugate base. Okay. So all of these, when you add a proton, it becomes a conjugate acid. When you remove the proton, now this is all short answer, when you remove a proton, it becomes the conjugate base. When you add a proton, it becomes the conjugate acid. Also, ranking acids. So if I give you the pKa and the Ka, okay, which is most acidic? Okay, the most acidic, again, this is short answer. You don't need, bring a calculator, but which is most acidic? You're going to find the one that has the lowest Ka or highest Ka, lowest pKa or highest Ka. Okay, this represents the most acidic. This is all short answer. Okay, you shouldn't need a calculator. Maybe you'll need a calculator for this one when you rank an acid, but all of these are true, false, or short answer. All Right, so there's also an extra credit problem. I won't go over it since it's extra credit, but it is calculating the pH at the equivalence point. So if you want to go over that, remember we use the back reaction, which can be either Ka or Kb. So if you want to go over those problems, either in your lab that you did, practice problem set, or the one we did in class, the practice one that's in our chapter 16. Okay, so the key points here is that the titrand is equal to the titrant, and you're going to use the back reaction, okay, which can either be Ka or either be Kb. All right, so I'll let you study that since it's extra credit, and we did do it in class, and we did some practice during your lab, that problem set. So, and then, yeah. All right, are there any questions or comments here? All right, so this is what I'm expecting. I'm expecting the test to be on Tuesday, and I think I should be able to be here on Tuesday morning. Yes, but there'll be no lab. Okay. So I'll let you guys decide, do you want to end the class now or do you want to go over the chapter 17? So if you go over chapter 17, we can finish earlier, which will give you, some days off or a class off in the future, because I need to get through chapter 17 and 18. If you want to end now, we can end now, but there'll be no break later. Once I get to chapter 18, you can have study time or personal time. So I'll let you decide because we got 15 more minutes. What do you guys think?
Do you have to take notes if we do chapter 17?
Yeah, gotta take notes. First of all, do I even have my notes here? Ah, yeah, here we go. What do you guys say or do or think? This is 8 pages, right? 9 pages. And we already went over a little bit of it, so let me just take maybe 10 minutes. Okay. All right, so this ends the material for exam 3. Okay. So make sure you also turn in your 16 homework, chapter 15 homework and chapter 16 homework. And then your quiz is due, okay, unless you want me to drop it. Okay, I can drop it. So let's just talk about thermodynamics here. All right, we have 3 main parameters. Okay, one is entropy, which is S delta S. This is disorder. The other one is H. It's always delta H. This is enthalpy. This is heat flow. Okay, and all of them bound together with delta G. Okay, this is called Gibbs free energy. Okay, this is a very big deal in biochemistry, and this is a big deal in the thermodynamics class that they teach here. So this Gibbs free energy is here. So this is the final arbiter. Okay, this is the final judge. Okay, so here, if the delta G, which takes input from enthalpy, and it takes input from entropy, and sometimes temperature plays a role in a reaction, but if this delta G is minus, we call that an exergonic reaction. This is where the products are favored. Okay, without its own volition, without you doing anything, the reaction will happen, okay, on its own. Okay, but remember, it's not just entropy that adds to it, but enthalpy. Okay, and if your delta G is positive, we call that an endergonic reaction. Okay, this requires energy. This requires energy. All right, Gibbs free energy is useful energy. Okay, this is energy that could be harnessed. Okay, this is energy that can be captured. Okay, so oftentimes they say, especially in thermodynamics, they say heat is given away. You can't harness heat. Okay, but whatever Gibbs free energy that is released, that can be harnessed. Okay, have you heard of ATP, the molecule ATP, if you're a biology major? Okay, if you're not, you may not have heard of ATP, but
I think I've heard of it, but the only thing I can think of is what is the at constant pressure kind of thing. That's the only thing that's coming to mind.
no, it's not. It's totally different. So. So energy to move a cell, energy to twitch a muscle fiber, solar energy. So this is all useful energy. This is all energy that can be harnessed or transformed into another type of energy. Okay, so energy from the sun can be transformed to solar energy, which could, I don't know, run your light bulb. Okay, ATP is a molecule in the cell. Okay, if you break down ATP, you have energy, and that energy doesn't just go away. Your cell will use that energy to, I don't know, move a cilia, move a flagella, move something, or move actin, or do something. Okay, so this Gibbs free energy, what I'm trying to tell you, is that it's energy that can be harnessed and captured. Okay, to do something. It's called use. It can do work. We call this work. I'll just say energy that can be captured to do work. Energy that can be captured to do work. And by work, I mean not heat. Okay, something that is useful. All right. So this is the equation. Okay, let's look at this. Okay, let's look at these four reactions with me here. All right, here we have a gas and we have a gas, two gases, so a total of three. It's giving you one gas and two liquids. Okay, we see the delta H is negative. Okay, so negative delta H is an exothermic reaction, and that is a reaction that's enthalpically favored. Okay, in terms of enthalpy, this is favored. Okay, enthalpy favored. Okay, what about entropy? You have three gases going to one gas and then two liquids. Okay, is that more order or more disorder? Okay, you're making your three gases, which are very disordered. Okay, you guys only told me, which is correct. A gas has more disorder than a liquid, which has more disorder than a solid, which is very ordered. Okay, this S stands for entropy. So what do you think? More order or more disorder? More order. Okay, so this would be entropically not favored. Okay, I'm talking about reaction 1. So will this reaction go? Well, it depends on the temperature, and it depends on, you plug in the entropy, you plug in the enthalpy, if the delta G is negative. Okay? And so some reactions can be enthalpically favored, some reactions can be entropically favored. If they're both enthalpically and entropically favored, this will always be negative. Okay, so what is S here? Or delta S, I should say. Negative, okay, because it's more ordered. Okay, what about this one here? Aqueous, aqueous going to liquid. Okay, what would the delta S be here? Positive or negative? Aqueous, what is aqueous? Is that more order or more disorder? H plus and water. That's more disorder. Okay, you have more stuff, more mass, more stuff, more things going on. That's more disorder. What is liquid? It's a pure substance. Okay, is that more ordered or disordered? Okay, I'd like to convince you that it is more ordered. So is this entropically favored? No, it's negative. We're making more order. Okay, what about enthalpically? Is it favored? The negative sign tells us it's favored. Okay, a negative enthalpy is called exothermic. Okay, a negative enthalpy is called exothermic. Okay, and the negative delta S change in entropy means it is non-spontaneous. Okay, more order, more order. How about this one here? We have a solid going to a liquid. What would you predict the delta S be, entropy? A solid going to a liquid, positive or negative? Which is more ordered? A solid is more ordered. Which is more disordered? Liquid. Okay, solid going to a liquid. What would your delta S be? Okay, you're making something that's more disordered. Okay, what would the enthalpy be? Positive. Okay, we call that an endothermic reaction. So in terms of entropy, okay, in terms of entropy, is this favored? Yes or no? Yes. Okay, things like to go towards more disorder, like your kitchen sink or like your bedroom. Okay. But in terms of enthalpy, is this favored? Yes or no? No. Okay, so we say this is enthalpically favored, entropically disfavored. Right? Enthalpically disfavored, entropically favored. That's what I meant. All right, so will this reaction go thermodynamically? Okay, you have to plug in the values, plug in a temperature. If it's negative, then yes, it will go to products. Because some reactions are enthalpically or entropically favored. All right, here we have a solid, one solid going to an aqueous and aqueous. Okay, solid going to a solids are very ordered, going to a disordered aqueous and another aqueous. Okay, what would the delta S be? Okay, it's tending towards more disorder. Okay, what do you think about the delta H? Endothermic. So just like the equation above, this is enthalpically not favored, enthalpically disfavored because of the positive delta H. But what about entropy? Okay, it's entropically favored. Okay, favored in terms of entropy. Why? Because we have a solid going to an aqueous. Okay, more disorder. Entropically favored. Okay, so these are the types of things we want to study in this chapter. Also realize we have something called standard state. Okay, this means standard state. Okay. Standard state conditions. It basically means that you can look up these values in the back of a textbook. Standard state is standard state conditions. I believe it's 25 degrees C. If you have a gas, it's at 1 atmosphere, and the reaction is conducted at 25 degrees. If you're having solutions, it's at 1 molar. So anyways, this knot represents standard state conditions. Yes, 1 molar. It's a very specific set of conditions. All right, let me quickly go through number 2 and let me see if I can get to page 3. If I get to page 3, I think I'm a little bit happy. Okay? Not very happy, but happy. All right, the reason why I'm going to skim through page 2 is because entropy is disorder, and the most disordered substance is a gas. Okay, what do I mean by disorder? Okay, let me tell you some buzzwords that talk about disorder. Okay, degrees of freedom, motion, rotation motion, vibration motion, translational motion. Okay, all of these. Have you heard of NMR? Okay, NMR can actually measure the speed. Okay, you have a, well, anyways. more motion, more degrees of freedom, more stuff, more mass. Okay, all of these things contribute towards a higher entropy. Okay, think of a gas, how disordered it is. Okay, think of a solid, how ordered it is. Okay, think of this in terms of entropy. This is more disordered than that. Okay, so we're going to put some numbers here, and that's called standard entropy, standard state conditions. Okay, these are numbers I'll give you on the exam. Okay, so you don't memorize it. One thing about entropy, you can either see this thermodynamic variable as S or delta S. This is a measure of disorder. Okay, this is a measure of disorder. Be positive or negative. So here's some values for S. All right. Remember, we're talking about standard state, and you can look up those values in the back of a textbook. Okay, we're looking for more disorder. The change in entropy will be positive. Right? If it's tending towards more order, like you clean up your sink, you make a solid in a chemical reaction, okay, you make less instead of going from 2 moles to 1 mole. All of these phenomena are associated with order, and that is a negative. All right, let's see here. Let's see if we can quickly do these, and then I'll see you all on a Tuesday. All right, condensing water vapor. Okay, more order or more disorder? Okay, what is condensation? What is condensation? Okay, on your car windows, okay, gas to a liquid. So what would delta S be? Negative. Very good. Okay. Forming sucrose crystals from a supersaturated solution. Okay, crystals. You know, crystals are very ordered. Okay, why are they so expensive? If you look at them under a microscope, okay, they're very, very ordered. So you're forming crystals from a solution. Okay, solute plus solvent. What do you think, positive or negative? Crystals. Okay, something that's very ordered. Okay, if you're forming crystals, that would be negative. Okay, crystals are very ordered species. Okay, from a solution. Solution is solute and solvent. All right, heating hydrogen gas from 60 degrees to 80 degrees. 60 degrees to 80 degrees. What happens when you increase the temperature? More order or more disorder? What do you think? If you increase the temperature? If you increase the temperature, more disorder. Remember, as you increase the temperature, okay, you're going to get more rotational motion, more vibrational motion, more translational motion, more collisions. All of this is associated with disorder. So heating something will increase the entropy. And then sublimation of dry ice. Okay, what do you think sublimation is? Okay, what is sublimation? Okay, it's a solid going straight to a gas, skipping the liquid step. Okay, have you ever had, oh my gosh, these chips, dehydrated things? You get them at Fresh Market. Banana chips. Banana chips. Ever had banana chips? Okay, what they do is they'll take the banana and then they remove the water. The water goes away as a vapor and you get these dehydrated banana chips. Okay, so that's what sublimation is, solid to a gas. In terms of entropy, is that positive or negative? Okay, positive. Okay, so when dry ice sublimes, it goes from the solid, skips the liquid, and goes to a gas. Okay, so these bottom two are tending towards more disorder. All right, I will see you all on Tuesday. Watch this recording, go over the practice tests, and I think you should be good for 2 star.